So we want to thank everybody for joining us, and we are excited that you are here with us. I am Michael Aguinaga with the Museum of Discovery and Science. I'm the Public Programs Manager, and I am honored to have Dr. Ada Sarajedini with us from Florida Atlantic University joining us today. Our topic being Hubble, and actually specifically photos that Hubble has taken, and these are some of the most important photos ever taken. And our host will go ahead and get us into those, but a little about him. First, we want to welcome all of our Leonardo da Vinci Society members to this event in partnership with the Florida Atlantic University College of Science. So Dr. Ada Sarajedini is the Dean of the Charles E. Schmidt College of Science. Before coming to FAU in January of 2017, he served as Associate Dean for Natural Sciences and Mathematics, as well as Associate Dean for Research in the College of Liberal Arts and Sciences at the University of Florida. That's a long sentence and title. Woo. Before that, he was Associate Chair and Acting Chair of the Department of Astronomy. After receiving his Ph.D. in astronomy at Yale in 1992, he spent 7 years as a postdoctoral researcher and a Hubble Fellow at Kitt Peak National Observatory and San Francisco State University. Dr. Sarajedini spent 2 years at Wesleyan University in Middleton, Connecticut as an assistant professor before moving to the University of Florida in 2001. He received an NSF Career Award in 2001, a University of Florida Research Professor Award in 2006, and was the principal investigator of a large treasury project with the Hubble Space Telescope starting in 2014. Dr. Sarajedini has over 500 publications, which have over 11,000 citations. Of these publications, over 200 have appeared in the peer-reviewed literature. His Hirsch index, according to Google Scholar, is 45. His research is focused on resolved stellar populations in local group galaxies. These include field stars, open and globular clusters in the Milky Way, M31, M33, I'm going to mess this one up, the Magellanic Clouds, thank you, and the numerous nearby dwarf galaxies. When we resolve individual stars in these systems, we can apply our knowledge of star formation and stellar evolution to understanding the process of galaxy formation and evolution. So with that being said, I just want to go over the questions and answers because everybody is muted right now. So if you do have any questions, feel free to put them into the chat. You can address them privately to myself or Hillary Wallace, or you can even put them in the general chat. We'll funnel them into our Q&A, which will be after Dr. Ada Sarajedini is done speaking. So with that being said, I think we're going to go ahead and get started. I'm going to turn this over to Ada. Ada, take it away.
Thank you very much, Michael. That was an excellent introduction. I'm going to attempt now to share my screen. So hold your breath. All right. So again, thank you for that introduction. I'm going to see if I can get, there we go. And I'm going to now just minimize. All right, great. So again, thank you for that introduction. It was very kind. And as Michael indicated, I've had a great deal of experience working with the Hubble Space Telescope. And I want to share some of that with you and talk about some of the most important photos ever taken by the Hubble Space Telescope. And as Michael indicated, I'm also a professor at Florida Atlantic University in the Department of Physics. Okay. All right, so to begin with, let's just talk about what science actually is. How do you do science? How do scientific investigations typically progress? Well, science is a tool to better understand the natural world. And it begins by taking observations. You ask a question, you take observations. Another word for observations is data. Data is meant to be understood. And so we come up with an explanation to understand what the data is saying, what it means. And another word for explanation is model, hypothesis, or theory. And every good theory makes a prediction. And predictions are then tested against the observations. If they come true, in other words, if the prediction and the observations are in accord, then the model is probably correct. If they don't, then we have to go back and change the model. And hopefully in this way, improve our understanding and our explanation of the observations and the data that we take. Now, astronomy fits into this model, or I should say this process, very well of how we do science. And I want to come back to it throughout the talk and just kind of remind you of this and show you how astronomy fits into this. So this is how we do science. Now, I also want to talk about the concept of the universe as a time machine. When we look out into space, we're looking back in time. Now, why is that? Well, because the speed of light is finite, 186,000 miles per second, or 300,000 kilometers per second. So for example, the moon, which is 284,000 miles away, is 1.5 light seconds away. The light from the moon takes 1.5 seconds to get to us. How about the sun? Well, the sun is just over 8 light minutes away. The light we see from the sun is 8 minutes old. At that speed, 1 light year is 6 trillion miles. And, you know, to our everyday experiences, that's a long way. But in the universe and in the galaxy, that's nothing. It's a very small distance when it comes to the scale of the galaxy and the universe as a whole. So when we think about looking out into space, we have to think about we're looking back in time. That means that the further away we look, the further back in time we're looking. And naturally, the fainter objects are that we're trying to study. The further away it is, the fainter it is. Obviously, it's going to be more challenging to study, but we want to look as faint as we can because that allows us to look back in time to the earliest history of the universe. Now, why is the Hubble Space Telescope so special? Well, the main thing about it is it's above the Earth's atmosphere. It's orbiting the Earth at about 350 miles, and the Earth's atmosphere is not in the way, and so the atmosphere, the blurring caused by the atmosphere is not there. It's non-existent completely. I'm going to show you some examples of what that means in a second. Plus, HST's pointing and tracking is incredibly good. As I say here on the slide, it could shine a laser beam on a dime 200 miles away and hit it exactly on the spot. That's how precise the pointing and tracking of the telescope is. And both of these factors are incredibly important when it comes to talking about the most important photos Hubble has ever taken, as I'll tell you in a second. And looking at this diagram here it's a picture of the optical assembly of the telescope. Just to go over this quickly, the light comes in from the left through the tube, bounces a couple times inside, and then ends up on the right side of the telescope where the instrument module is. And in that little box at the end of the telescope on the right is where all the instruments are, the cameras, spectrographs, polarimeters, and all those kinds of things. And then you'll see the fine guidance sensor, which I indicate here with the mouse. That is actually the box that ensures pointing and tracking of the telescope at the level that we will need it to in order to take these images that I'm going to be talking about. And of course, here's a person for the relative size. Here's some examples of ground-based pictures taken from the ground on the left compared to the same object with a Hubble Space Telescope. So at the top, it's a galaxy. On the left, you can see a ground-based image. On the right is a Hubble image. And obviously, the HST image is much sharper and easier to resolve the stars than the image on the left. On the lower part, I have a globular cluster. This is the globular cluster M15. On the left is a ground-based image. On the right is a Hubble Space Telescope image. It's not as obvious in this case, but trust me, those stars on the right are much easier to study because they're better resolved than the ones on the left on the ground-based image. This gives you an example of just how stark the contrast is between ground-based imaging and Hubble Space Telescope imaging. So that's one of the reasons why it's important that HST is above the atmosphere. Now, this graphic was released about 5 years ago when HST was celebrating its 25th anniversary. Well, this year, it's actually its 30th anniversary. It's been in orbit for 30 years, imaging the sky and taking data. And this just shows some basic information about the telescope. The most important one from our standpoint is that it's above the atmosphere, 350 miles above the Earth, and it generates about 10 terabytes of new data every year. And every single observation of the telescope ever taken is archived on the ground at basically disk drives at the Space Telescope Science Institute in Baltimore. And because all of you out there, all of you taxpayers, you paid for this, those observations are available to anybody in the world who wants to access those data. They're there. Now, moving on to what our actual topic is, which is these most important photos ever taken. And the first one is called the Hubble Deep Field. And the idea here is that a part of the sky was chosen that was apparently blank. And HST stared at this part of the sky for 10 consecutive days in 1995. Took over 340 individual exposures of this part of the sky, and they were all added together to make a very, very precise, very deep observation of that part of the sky. And this shows the Big Dipper, the North Star, and that red dot is the location of the Hubble Deep Field, which was the first set of observations like this. Now, the next one shows you a little animation of where this is located in the sky. And you can see we're zooming in to what is apparently an empty part of the sky, but in reality, we see this. And so this is the first Hubble Deep Field. It was taken by HST in 95 and using what they call the Wide Field Planetary Camera 2. That's the instrument, WFPIC 2 for short. And what you see here is mostly you see galaxies. There's literally thousands of galaxies in this very small part of the sky. Everything else are stars. There's a few stars here, and you can tell the stars because they're the ones that show diffraction spikes. So for example, this is a star right here, which is a point source, but with diffraction spikes, this kind of star-like pattern, this four-pointed star-like pattern on the star itself. And there's a few stars. Here's another one over here. There's one right there that I showed earlier. There's one in the middle. There's probably a handful, maybe 10 or 12 stars in this entire image. Most of these fuzzy objects are distant galaxies. So it was a good idea, so let's do it again. So in 2003, a field was chosen in the southern hemisphere in the direction of the constellation Eridanus or Fornax. So this is a map showing the direction, the location of the Hubble Ultra Deep Field, this time in the south. And in this case, separate exposures over 4 months in 2003 were taken, hundreds of them, and combined together to form what is now called the Hubble Ultra Deep Field. And here it is. So once again, you see a lot of fuzzy objects, thousands of fuzzy objects, all of which are individual galaxies. And you see a few bright stars, again, the ones that show these diffraction spikes, the cross-like pattern, which are the diffraction spikes caused by the telescope's infrastructure. And only stars show those. Everything else that's fuzzy is a galaxy. So of that Hubble Ultra Deep Field, there was a smaller collection of exposures taken out of that that represents 2 million seconds of exposure time. And this is the extreme deep field. And this just shows you the size of the Hubble Ultra Deep Field and the extreme deep field compared to the full moon. These are very small parts of the sky. And yet there are thousands, in some cases, tens of thousands of galaxies in these little parts of the sky. And as a reminder, each of these galaxies, these fuzzy things, is akin to our own galaxy, the Milky Way. Our galaxy contains 100 billion stars. 100 billion stars. And the galaxies you see here are between 10 times smaller to 10 times larger than our own galaxy. So what we're seeing here is literally hundreds of billions of stars right here in this one image, all organized into these fuzzy objects we call galaxies. You also notice that the galaxies come in different colors. So if you see there are some that are bluer or maybe white, say, there are some that are yellow, and there are some that are red, and there are some that are extremely red. And next I want to talk about why those galaxies are red and what that means about the universe as a whole. So here's some of those galaxies. These are, again, this is the ultra deep field, and these squares, inside each square is a galaxy, a fuzzy object. And on the right, you see kind of cutouts, thumbnail cutouts of each of those galaxies. And you can see how they all look red. Well, what does that mean? What does their color actually mean? So what they look red? What does that actually imply about the galaxy itself? And to get a better sense of that, I need to talk a little bit about the Doppler effect. This is something that's been known for a long time. And what it is, and this illustration shows that this train moving to the right, the observer over here on the right hears the train's whistle or the sound. And when it's moving toward the observer, the train sounds like it has a higher pitch to its whistle or its horn. Where it's moving away from the observer, it has a lower pitch. So what's happening is that the sound in the direction of motion is being compressed, and in the other direction, it's being expanded. And so the observer that the train is moving toward basically hears a higher pitch. Well, this is how sound behaves. Well, light, which is also a wave, behaves in the exact same way, in the sense that when an object is moving toward you, the light from it appears bluer than it actually is. When it's moving away from you, it appears redder than it actually is. And this is what we call redshift. And that's shown in the next slide. So here we have galaxies. So in the middle, you see from the top to the bottom, different galaxies in the sky. And then on the left, you see the light from that galaxy dispersed into its component colors. The colors are not shown here, but the blue colors are on the right, and the red are on the left. And what you see here is that from top to bottom, these are galaxies that are moving faster and faster away from us. And what happens to the light from them is the light appears redder and redder as you go from the top to the bottom. And the numbers you see there are actually in kilometers per second, which is the velocity of that galaxy moving away from us. The upshot here is that this concept of redshift has to do with the fact that when galaxies move away from us, their light becomes redder. And it's a version of the Doppler effect. In terrestrial environments, the Doppler effect is manifest in the changing of the pitch of sound of objects moving toward and away from you. But in the galaxies in the universe, it's manifest in the redshift of the light. And what you see here then is that redshift is defined, and you don't need to worry about this math. The bottom line is that the letter Z is used to represent redshift, and the faster something is moving away from us, the redder the light appears. So that's one observational fact that we need to keep in mind. And the next observational fact is shown in this slide. And this is a plot, actually, that was made by Edwin Hubble in the 1920s. And what he found is that when he measured the velocity of galaxies moving away from us, he found that the ones further away were moving faster. And this diagram shows distance on the horizontal axis, velocity on the vertical axis, and it's a very nice straight line. And all that to say that galaxies that are further away are moving faster away from us. So in other words, the redder a galaxy appears, the further away it is. And as I show here, how red the galaxy appears indicates its distance. The redder it appears, the further away it is. And that's really just an expression of what's called Hubble's law. And what it says is that no matter what direction you look, the galaxies are moving away from us. Galaxies are moving away from us. The further away they are, the faster they're moving. And remember, When you look out into in the universe, you're looking back in time. So the further away they are, the faster they're moving. The further away they are, the further back in time you look, the faster they're moving. So that's an important point here. Now, getting back to this slide. These galaxies here are red. Why? As we just learned, because they're very far away. Their redshift is causing their light to appear red, and the redshift, how fast they're moving, is related to their distance. The redder the galaxy, the further away it is. So we're looking at some very distant galaxies. And what you notice is that these red smudges are really just smudges. They're really disorganized, kind of ugly looking things. They're not very well put together. They're kind of naughty and disorganized. And what that indicates is that galaxies that are very far away, the ones that look red, are not as well organized as the ones that are not so red and that are very nearby. And so what we can do then is kind of use this as an indicator of how galaxies look over time. And that is to say that the nearby ones look very well put together. They look spiral, they look elliptical, they're organized, they're beautiful, if you will. And the ones that are far away, the ones that are red, are less organized. They're more smudge-like. They're not as well put together. They're more disorganized. And that's really an expression of what we're finding with respect to how galaxies form, how they're put together, how they form and evolve over time. And so this picture is what's come out of some of the work with the Hubble Deep Field. And what this picture shows is on the left, we have galaxies today. So these are ellipticals and spirals today. The universe, we think, is about 13.7 billion years old. So that's why it says 14 billion years on the left. And then as you go to the right, you have 9 billion years, 5 billion years, and 2 billion years. And what you see is that as you go further back in time, and remember, we're looking very far away. The further away you look, the further back in time you're looking. And as you go further back in time, you see the galaxies look less structured, less organized. They're not as pretty, not as put together, if you will. And what this indicates is that over time, large galaxies like the Milky Way, like the spiral over there, are formed through the process of smaller galaxies coming together, colliding with each other, sticking together, and assimilating, agglomerating, if you will, into these very large galaxies like the Milky Way. So galaxy formation is a process of taking small galaxies, we call them dwarfs, and colliding them with each other. And in some cases they stick, in some cases they don't. And we're talking about hundreds, thousands of these dwarf galaxies colliding with each other to form larger galaxies like the Milky Way and the spiral and elliptical that you see on the left side of this slide. That's the process of how large galaxies form. Now, here's an example of a nearby galaxy, the Andromeda Galaxy. And it's a beautiful spiral, very well put together. It happens to be 2.2 million light years away. So the light we see from it left it 2 million years ago. But this is nearby. This is actually in our own neighborhood, our own backyard. And what you see is a very well put together, organized galaxy, but you see two nearby dwarf galaxies that are the leftovers of the process that formed this large spiral galaxy. And I just indicate them there with those ovals. These are two dwarf galaxies left over from the process of the formation, that the process that formed this galaxy, Andromeda. There were literally hundreds, thousands of these little galaxies that went into forming Andromeda, of which there's about half a dozen, well, actually more like 10 or so that are left over from that process. And that's what we're talking about in terms of dwarf galaxies coming together to form larger galaxies like the Milky Way. I should note too that Andromeda looks like the Milky Way. If you were able to photograph our own galaxy and from outside and look back on it, this is what it would look like. And we also have our own system of a couple dozen or so dwarf galaxies that are left over from the formation of our own galaxy, just like this. If we could look back on the Milky Way, it would look very similar to this picture that I show here of the Andromeda Galaxy. So this slide just kind of shows what we're seeing with these deep fields. On the left, we have HST looking out into the universe. And as I said, the universe is 13.7 billion years old. And when you look nearby, that is to say, out to a few million, say, light years, those are the normal galaxies that we see nearby. And then that first magenta line is the Hubble Deep Field. That's how far back in time we are looking in terms of the Hubble Deep Field and where it looks. So that's about a billion years after the Big Bang. I can talk more about this later if you'd like, but we think the universe was formed by this very large explosion called the Big Bang, 13.7 billion years ago. And so after the Big Bang, a billion years after that is when the galaxies in the Hubble Deep Field that we see have formed and have come together. And then the Hubble Ultra Deep Field now goes back to between 0.7 and 0.4 billion years after the Big Bang. We haven't even got to the first galaxies yet, because the first galaxies are beyond the horizon, if you will, of the ultra deep field. And the first stars are even before that. And then we're getting into the early few 100 or 200 million years after the Big Bang, where we see what we call the dark ages and the radiation era. And of course, the Big Bang is way over to the right. So to go that extra mile to see the first galaxies is going to require, and I'll show you in a second, the next generation of space telescope. So here's what we have. So these are different ways of probing the early universe. And as I show this and discuss it, please keep in mind that as you look back, as you look out in the universe, you're looking back in time, but you're also needing to see fainter and fainter objects, because the further away it is, the fainter it is. And so the harder it is to actually observe and measure the properties of those objects. So at the top, in the 90s, we had these fairly large ground-based telescopes. And so they go back to about 6 billion years after the Big Bang. And then the Hubble Deep Field takes us to about 1 to 1.5 billion years. The Ultra Deep Field to about 800 million years. And then the next ultra deep field in the infrared, which I haven't talked about, but obviously that was the next step, to about 500 million years. And then we're looking to the James Webb Space Telescope to take us hopefully as close as we can get to the first galaxies, and hopefully, if we're lucky, the first stars that have formed. And the difference here is that the ground-based observatories, the largest ground-based telescopes now, are 10 to 11 meters across. Now, this measurement represents the size, the diameter of the primary mirror, the mirror that gathers the light from the sky. And the largest ground-based telescopes right now are about 10 meters across. Now, those are on the ground. Remember, they're contaminated and debilitated by the atmosphere. The atmosphere blurs things. So when you go above the atmosphere, you gain a lot in light gathering power for not much aperture size. So the Hubble Space Telescope is only 2.4 meters across in the size of the primary mirror. The largest ground-based telescopes are 10 meters. HST is only 2.5. And so by pushing the Hubble Space Telescope's capabilities as deeper and deeper and deeper to a greater degree, we were able to push the horizon of observations back to about 500 million years after the Big Bang. But we've pretty much reached the limit of what HST can do in terms of depth and going back in time. So the next generation James Webb Space Telescope, the primary mirror on James Webb is 6.5 meters across. So it's going to be obviously in space above the atmosphere, and it's going to be in a different kind of orbit than HST. It's going to be able to stare at a certain part of the sky for an indefinite amount of time. HST is in a low enough orbit that the Earth actually gets in the way of the sky occasionally. And so it can't really stare at a particular part of the sky indefinitely, whereas James Webb Space Telescope can. And so with 6.5-meter mirror above the atmosphere in space, we're hoping that we're going to push the limit of what we can see back to the first galaxies, well beyond basically well beyond where we are with the Hubble Ultra Deep Field. And again, James Webb was supposed to launch 2 years ago, but it's been delayed and further delayed, and it probably won't launch until 2021. So hopefully, when it gets up there and gets deployed, we can actually start taking some observations with it next year, maybe even 2022 if things don't go quite right. Now, this graphic just shows, kind of shows the history of the universe in a different way. And this is, unfortunately, it's a bit flipped. On the right is the present day. And as we go back in time, we're looking to the left. So the universe is 13.7 billion years old. And as you look back in time, you're seeing the earlier and earlier galaxies. And you see the first stars, and again, the dark ages. And what you're seeing here on the very left, the afterglow light pattern, that kind of colorful vertical plane, is what's left over from the Big Bang. And that's what it looks like. So this is called the primordial background radiation. And what this represents, the colors represent temperatures in the sky. The red areas are a little warmer, and the blue areas are a little cooler. But what you see here is temperature also represents density. And so what you see here are different parts of the sky that are a little warmer and a little cooler in this primordial background radiation. And I'm going to talk a little bit about what that is here. So this radiation was discovered in 1964 by these two gentlemen, Penzias and Wilson. And they used this big antenna that's behind them to actually discover this very, very, very low intensity radiation. It's all over the sky. It's called the primordial background radiation. Primordial, because it was from the early universe. Background, it's all over the sky at a very low intensity. And radiation, it's a form of light. It's also called the cosmic microwave background. And so the idea is that the Big Bang happened here on the left. The universe expanded very quickly. And what you see here, this pattern of colors, is what's left over from the initial very high temperatures of the Big Bang. The Big Bang represents everything in the universe, everything you see around you, your house, your car, the building you're in, everything was scrunched, crunched down, contracted, compacted to a very, very small point. So you can imagine the Big Bang was an incredibly hot entity, incredibly hot. The universe was very hot, tens of thousands of degrees. And the Big Bang the universe expanded, it cooled off, and over time, it cooled off from thousands of degrees to what it is today, which is about 3 degrees Kelvin. Remember that absolute zero is 0 Kelvin. That's where all molecular and atomic motion stops. Well, the microwave background is at 3 Kelvin. And so we're not going to see that with HST, but what we want to do is get as far back in time as we can to the time when we can actually probe the properties of the microwave background soon after the Big Bang happened. And as I say in this slide, James Webb Space Telescope is going to help us get closer and closer to when the first galaxies and the first stars formed. So, and we can talk more about this in the Q&A session if you'd like. So these are my main takeaway points from this presentation. HST, the deep fields, the Hubble Deep Field and Ultra Deep Field, they revealed the morphologies of galaxies. That is to say, how galaxies looked in the past, about 500 million years after the Big Bang. And they show that galaxies were much smaller and less organized. And not as put together, let's say, as modern galaxies, the ones we see nearby that are close to us. And so what that says is that this process of galaxy formation started with many, many, many thousands, in some cases, dwarf galaxies that were orbiting each other and collided with each other, and in some cases stuck to each other. And as they stuck together, they created larger and larger galaxies like the Milky Way. And over time, galaxies like the Milky Way and Andromeda were formed through the process of these dwarf galaxies colliding with each other and creating larger galaxies like the Milky Way and Andromeda. That is the takeaway from the observations of the Hubble Deep Field and the Ultra Deep Field. I have a few more slides to show, but I'm going to just stop there and take your questions.
Okay, so I do have a few questions to ask. And then you'll show the rest of the slides. Is that what your plan is?
Well, the slides are there in case I need to use them for answering the questions.
Gotcha. Okay, so I'll start it off. The first question that we have are, what are NASA's plans for the next space telescope?
Okay. So this shows it right here. This is the James Webb Space Telescope. And as I mentioned earlier, it's going to be 6.5 meters across for the primary mirror. When we talk about telescopes, a lot of people get confused that maybe magnification is the important factor to keep in mind. But really, professional telescopes, magnification isn't important at all. It's actually the size of the primary mirror, the main mirror that gathers the light that is then studied to reveal the nature of the universe. And so the larger the primary mirror is, the more light you're able to gather, and so the fainter you can see. And the fainter you can see, the further away you can see. The further away you can see, the further back in time you can see. So those are all connected to each other. And the plans then are for James Webb Space Telescope to be launched next year, and to be in high, to be well away from the Earth, so it's not going to be obstructed by the Earth's by the Earth itself, and so it'll be able to stare at different parts of the sky continuously, and just do many and several of these very deep fields, and hopefully get us back in time to when the first stars and the first galaxies formed. At the moment, that is really the holy grail of cosmology, which is figuring out when the first stars and galaxies formed. That's the plan.
Okay. The next question comes from one of our viewers. So it's here it is. Are there any Z-stack photos of the universe where we can see all of these things in one image? And where to find it? And then the second kind of part to that question includes, is there any implications from any of this work?
Could you repeat that, Michael, about Z-stacked images?
Yeah, so is there any Z-stack photos of the universe where we can see all of these things in one image?
So the interesting thing about the two deep fields is one is in the north and one is in the south. They're completely different fields. So yes, you can find images, Z-stacked images of the two fields on the web. I mean, they're all over the place. That's where I found the graphics for this talk. So they're quite common. It's just that you'd have a hard time finding stacked images that are a subset of all the images taken for the deep fields. The deep fields were taken intentionally to be combined. So you're not going to find any subsets of those combined images. You'll only find the final combined image of all the images together. So that's the one limitation. But they're quite common on the web. You can easily find those stacked images.
All right, our next question is from Ivan. So would galaxies appear more blue and slow if you were near them? Also, if you could use the telescope to see billions of years away, are you able to look closely into nearer galaxies to see if there are planets and what is on them?
Right. So let me address the first one first, which is, and I'll just show this this diagram here. So this is a cartoon, really, but it is based on real data. And what you see here is that the nearest galaxies to us are moving away from us, but not at not very high velocity. Now, these velocities here, these speeds, 20, 30, 40,000 kilometers per second. I mean, to us, that seems like really fast, but it's not. The universe is actually expanding at a much faster rate than what you see here. So the nearby galaxies are not moving as fast as the ones that are further away. And clearly, it's easier to study the ones that are nearby compared to the ones that are further away. So if you want to look for planets, we want to really look at the detailed structure of galaxies. You want to look at the nearby ones, the ones that are only 10 or 20 million light years away. Those are the ones that are going to be, in other words, those are the ones right here in the very lowest distance range of this diagram. That's where you want to look for, if you were interested to do that kind of thing, to look for planets and the more distinct structure of the galaxies themselves. And there's hundreds of galaxies like that, in that distance range. But I should say that, I mean, as far as looking for planets, we've really only looked at stars in our own galaxy, the Milky Way. The Milky Way is about 100,000 light years across. 100,000 light years. That's actually pretty small on these scales. So those stars are relatively bright, and we can study them in different ways to look for planets around them. And those are really the only ones that are amenable to those kinds of studies, because the rest are just too far away at the moment, which is to say that they're just too faint. We don't have a big enough telescope yet. I should say too that this in this slide, I mentioned that the ground-based telescopes we have today, the largest are about 10 meters across, but we're currently designing telescopes that are 20, 30 to 40 meters across for the ground. These, again, this number is the diameter of the primary mirror. And the larger the primary mirror is, the more light you can gather and the fainter you can see. So the ground-based telescopes are actually trying to get as large as possible to hopefully augment some of the observations taken by the James Webb Space Telescope, that's out in space. So they're really going to be working together in many ways. But the ground observatories certainly aren't standing still. I mean, they're also extending their reach by building larger and larger telescopes with larger and larger size primary mirrors.
All right, my next question is, why doesn't gravity, which warps space and time, get in the way of these direct observations?
Okay, the reason is this, that, so let me go back to this slide here. For these really nearby galaxies, I'm sorry, I should have said parsecs is another way we measure distances. 1 parsec is 3 light years. So take these numbers and multiply them by 3 if you want to know what they are in light years. So gravity on those kinds of, at that level of effect, is really only important for the very most distant galaxies, the ones where we see their light through a lot of intervening material. The galaxies that are nearby in the hundreds or millions of light years are not actually affected greatly by gravity. Now, having said that, there are small effects that do affect the light from these galaxies. And so we know how that works. We can take those into account. As it turns out, the Einstein theory of relativity, which governs how gravity affects light, has been tested back and forth, and it passes the test every time it's been tested. And so we use our expectations from the theory of gravitation from Einstein to correct any observations we have for the effects of gravity over those very long distances. And I should note, going back to my original slide about how science works, the theory of relativity, which is what governs the effect of gravity on light, which is the explanation here, the theory, it's been tested back and forth with predictions and then with the observations so many times. And every time it's come through with flying colors. In other words, the model, the theory of gravity, the theory of relativity, the predictions it has made have been borne out by the observations and the data every time that they've been tested. So we understand gravity, or at least we think we do, very, very well on small scales and large scales. And those corrections, that understanding has helped us to, make the corrections we need to our data based on how gravity affects light. So we know how it works, and we use the theory to make corrections based on that.
All right, our next question is, how is time different in the galaxies in comparison to Earth and or our galaxy?
How is time different?
Yes.
Okay. So let me go back to this here. I'm just going to show one of these last slides here. Okay. So on the lower part of this graphic, you see time after the Big Bang. Okay. And then just above that is redshift, that Z number that I mentioned to you earlier. That's how much galaxies' light is shifted to the red. So 1, 4, 5, 6, 7, 10. And what you'll notice is that this is not a linear scale. We go from 1 to 10 in a factor of 10 between 6 billion and 480 million years. So this is not a linear scale. What this is saying is that time, while it progresses linearly, its effect on redshift is not linear. And which is to say that, if redshift increases by a factor of 2, time doesn't increase by a factor of 2. That's what I mean. And so this correlation between redshift and time is something that's built into the models, the theory of the Big Bang and how the universe has expanded and changed its properties over time. And again, this correlation is all based on this theory, the theory of how the Big Bang happened and created the universe. And going back to my scientific method, that theory has been tested back and forth in terms of its predictions and what the observations show. And so far, what we see in terms of the predictions are borne out by the observations. So that's all good. Could it be wrong in the future? Yes, of course. That's how science works. Science is a self-correcting process. And so that self-correction could take a week, 10 days, 20 days, a month. It could take years. It could take decades. But that's the way science works. It's a self-correcting process. All that to say that the model we have for how the Big Bang happened and how time progressed and how redshift was dependent on time works very well. And the predictions it makes are borne out by the observations.
Our next one comes from Mark. Are we in the middle of the universe? Why is every other galaxy going away from us?
Okay, very good question. And that's what this diagram here shows, that every galaxy is moving away from us, and the ones that are further away are moving faster. The ones that are further away are the ones that we're seeing earlier in the history of the universe, which means the universe was expanding faster in the past. Okay, that's how the Big Bang is. We think that's how it works. But it does not mean that we're actually in the center of the universe. And there is no such thing as the center of the universe. And the analogy I like to make is made by, by pretty much all introductory textbooks, is that think about a loaf of raisin bread. A loaf of raisin bread, right? It's not in the oven yet, and there's raisins inside it, right? You put it in the oven, and it rises, it expands. And if you're on a raisin, you see every other raisin moving away from you. But that doesn't mean that you are in the center of this loaf of bread. So that's the analogy we like to use. things are moving away from everything else. But that does not mean that we are at the center of the universe. And if you look at it geometrically in terms of the models, the cosmological models, there's no such thing as the center of the universe. It's as if we're in this big raisin bread with raisins moving away from each other, but we're not in the center. So that's the best I can do for an explanation.
Our next question is, can Ada talk about why finding all these galaxies in the deep field photos are important, and what will this data be used for?
Okay, so these fields were chosen to be blank. These fields were chosen to be blank, to have nothing in them. We knew there were a few stars, but we had no idea that there were all these thousands of galaxies in these fields. And I'm just touching, this is really just the tip of the iceberg, for lack of a better term, because these observations led to enormous amounts of follow-up data taken of each of these galaxies by other telescopes. So there's surveys being done and have been done of the galaxies in these fields, all the different properties of these galaxies. And I've just touched on one, which is the appearance of the galaxy and how they tell us about the formation of how galaxies come together. But there's been many other studies done on the individual objects in these fields and what they tell us about the galaxies and about the universe as a whole. So while this area of the sky was thought to be empty, it turns out there's thousands, if not tens of thousands of galaxies in each of these fields. The other thing I should point out is that if you looked at this is the Hubble Deep Field. If you look at this is the Ultra Deep Field. Qualitatively, they look the same. They look the same. They have a lot of galaxies in them. They're fuzzy. They're different colors. They have a few stars, but qualitatively, they look the same. So this is the deep field. There's the ultra deep field. They look the same. What does that tell you about the universe? Well, it tells you that no matter what direction you look north, Hubble Deep Field. You look south, the ultra deep field. They look the same. The universe looks the same no matter what direction you're looking. And this is the centerpiece of two principles of cosmology. One is known as the principle of homogeneity and the principle of isotropy. Homogeneity says that the universe is smooth and homogeneous on the largest scales. Isotropy says that no matter what direction you look, you're going to get the same answer with respect to the properties of the universe. If you want to get the age of the universe, if you look in this field, the ultra deep field, and this field, the deep field, which are in the north and the south, you better get the same answer, because that's the idea. And so the fact that these two fields look the same qualitatively and quantitatively indicates that yes, the universe is homogeneous and it's isotropic.
Next question is from Nadia. It says, for a novice astronomer who is interested in looking up at the galaxies, do you have any recommendations for which type of telescope would be best to get started with, considering the Hubble is a bit out of the budget?
Right. So Hubble is a multi-billion-dollar instrument, right? And James Webb is closer, just over 10 billion. Actually, it's probably gotten the budget overrun, so probably taking it closer to 15. But I would actually just start with a cell phone app, because there's multiple apps online that you can download that will show you what this, the sky. It'll allow you to get around the sky and figure out what constellations are where the planets are, where the moon is, where interesting star clusters are and nebulae and that kind of thing. I would actually start with that. And that would be kind of the simplest, and these apps, many of them are free, the simplest way to kind of get familiar with what's up in the sky. As far as telescopes are concerned, that's a tougher one, because there are so many different kinds of telescopes, designs, manufacturers, sizes. There's so many different ones. It's hard for me to give you advice here, online in this forum. I think what I would say is, look at there's two major magazines in the amateur astronomy realm: Sky and Telescope and Astronomy Magazine. They come out every month. They have all kinds of ads and articles about how to buy the best telescope for your needs. There's articles online about this topic. There's all kinds of nuances to what exactly you'd like to look at, where you live, how much you're willing to spend. There's all kinds of factors. And so it's really hard for me to give you much good advice here. All I would say is that start with the app, learn your way around the sky, figure out what kinds of objects you're interested in looking at, and then do a little homework online to see what kind of telescope in terms of size and manufacture and specs are more in line with what you're interested in looking at.
Our next question is, what are you most hopeful for the John Webb Space Station to discover or confirm in the near future?
Right, good question.
Or
So
James Webb, sorry.
That's all right. So this goes back to this slide here. I really want James Webb to see the first stars. So here they are. We're at the Hubble Ultra Deep Field. We have to go to the first galaxies and the first stars. We want to see the first dwarf galaxies coming into being and forming their first stars. Now you might ask, well, can't we see those nearby, like near the sun? The answer is yes, we can. We can see old stars near the sun. Let me just go back to this for a second. Sorry, one more here. So this diagram illustrates one more thing about the universe, and that's this. When the Big Bang started, when the Big Bang happened on the left, the universe was composed of almost exclusively hydrogen and helium. Nothing else. All the other elements, the carbons, the nitrogen, oxygen, aluminum, uranium, all that stuff was formed in stars. Now, astronomy, we're fairly naive chemists. And in astronomy, we have hydrogen, helium, and everything else. We call everything else metals. A chemist would probably be mad at me for saying that, because to chemists, those are not metals. Okay. But astronomers, we call them metals because they're the ones that are formed after the Big Bang inside stars. Now, mind you, they're a very small fraction of the universe. In the sun, most of the sun is hydrogen and helium. 98% of the sun is those two elements. The rest of the sun, the 2%, are metals. Everything else, carbon, nitrogen, oxygen, aluminum, bromide, everything else in the periodic table is produced after the Big Bang. And it's a minority of the universe. But why am I talking about it? Well, because if we can find a star near the sun with very, very low amounts of metals, what that tells us is that it was formed very early in the history of the universe. That's what we're trying to do right now. That's another way to probe the earliest and first stars formed in the universe, is to look for the stars with the lowest amount of those heavier elements that we know and love in the periodic table. And so at the moment, we have actually found stars that have those heavy elements that are 1 million up to 10 million times lower than the sun's value. That's a very small amount of metals. And we think that those stars were the first ones formed after the Big Bang. But we have not found stars with zero metals yet. And that's another holy grail, if you will, in studying the early history of the universe, is stars with no metals, or basically the Big Bang fraction of metals. We haven't got there yet, but that's another direction that people are going to probe the earliest history of the universe.
Our next one is, what are the differences between the spiral galaxies and the elliptical galaxies?
Very good question. So this slide on the left, you see the two types. 90% of galaxies are either ellipticals or spirals. And there's, besides the obvious morphological difference, spirals have spiral arms, they're flat, they're, they have, they're flattened planes with arms. Ellipticals are round or elliptical in shape. The main difference beyond that is that elliptical galaxies are mainly contain old stars that are formed soon after the Big Bang. Spiral galaxies, on the other hand, have a range of ages in their stars. There's old stars, there are young stars, there's stars forming right now. There's regions of gas and dust where there are new stars forming as we speak in spiral galaxies. The Milky Way is a spiral galaxy. So actually the Andromeda Galaxy is a spiral. And you can see here in this picture that there's all kinds of gas and dust in the disk and kind of regions of red and kind of blue and yellow. And those are what we call H2 regions, which are areas of gas and dust that are forming new stars. And by new, I mean there are literally new stars being formed right now in this galaxy. Now, remember, when I say right now, I really mean 2 million years ago, because that's when the light we see from it left it. So, but in 2 million years is nothing in the history of the universe. So it's basically right now. So this is a spiral. Now, the two galaxies that are dwarfs that are near it are actually elliptical in their shape. So they tend to be older stars, older populations where there's very few, if any, young stars formed in those dwarf elliptical galaxies. The main difference being ellipticals are older, they tend to be older, spirals tend to be younger in the mean.
Our next one is, if the galaxies are moving away, where are they going?
Okay, good question. So when we say galaxies are moving away from us, what we really mean is not the galaxies themselves, but space itself, the fabric of space. Einstein told us that space actually is a thing. It has structure, it has form, it expands, it contracts. When the Big Bang happened, the expansion was not of the galaxies, but of space itself. And the galaxies are attached to that space. And so when the space expands, the galaxies also expand. And so when the universe expands, it's creating space. It's not expanding into nothing. It's actually creating the space itself. And I think the best way to think about this is when you blow up a balloon. Think of the universe as the surface of the balloon. And when the balloon expands, you're actually stretching the space. It's actually getting larger and larger, stretching space, increasing the distance between galaxies. And so think about the universe as a multi-dimensional entity, and you're looking at it on 2 dimensions. And so this balloon is expanding into another dimension that we can't perceive, but we're on the surface of it. And what we perceive is this elastic space that's expanding and contracting. So that's really the way to think about the expansion of the universe, is space itself is expanding and being created, if you will, as the universe expands.
Our next question comes from, so the question is, so does this mean there are other humans walking around on these planets within these galaxies who are mirroring our lives and just like us?
The short answer to your question is yes. Yes. Look at this image. This is the ultra deep field. There's 100, so let's just say there's 1,000, 10,000 galaxies in this picture. Each galaxy is like the Milky Way. Just assume that. The Milky Way has 100 billion stars. Okay, so 100 billion stars per galaxy. And there's 1,000 galaxies here. So now you're looking at 100 billion thousand galaxies. All right, and all these stars in each of the, 100 billion thousand stars, in this image. And they're stars. I mean, they could have planets around them. I mean, we know from our observations of nearby stars around the sun that we've already discovered, thousands of stars with planets around them. So imagine if we were able to probe our entire galaxy of 100 billion stars. Imagine how many planets could be going around those. And now expand that to all these galaxies that we see in this picture. The odds are that there is some life somewhere else, around some other planet, around some other star, in some other galaxy, just given the numbers. And beyond that, it's really just a question of philosophy in terms of what you believe to be the nature of the universe. In terms of the numbers, there's plenty of probability that, yes, there are people somewhere in one of these galaxies in a planet, on a star, in a galaxy, and we're in this picture looking out in the universe from their vantage point, asking the same questions we are, and trying to hopefully get the same kinds of answers that we are. But again, it's hard to know because the only kind of life we know about is us. Carbon-based life has evolved on the Earth. That's all we know about. There could be other kinds of life out there. We just aren't familiar with, the nature of that life. And so we're limited by obviously our own perspective of what we think life is like and what it does and how it operates. But just based on that, there's a very good probability that there are planets around these stars in these galaxies where life exists.
So somebody's taking this the other way, and I like this. So are there galaxies that are further into the future than us?
No.
Okay.
We cannot see into the future. We can only see into the past. And we see into the past by looking very far away. The future is being created as we speak. So there's no such thing as looking out to see the future.
Next, so although everything is moving away from us, is there any possibility of a dwarf galaxy becoming part of the Milky Way?
Yes, there is. Actually, it's happening right now. I don't have any slides for this one, but in 1994, a galaxy was discovered that was actually falling into the Milky Way right now and becoming part of the Milky Way galaxy. Being assimilated, if you will, if you're a Star Trek fan, into the Milky Way. And this was a huge, I would say, tremor, in the scientific landscape, because people didn't expect to be able to see this process in live action, in our backyard. If you want to do a Google search on it, it's called the Sagittarius Dwarf Galaxy. And it's in the constellation of Sagittarius. The Sagittarius Dwarf Galaxy. It was discovered in 1994, and ever since then, astronomers have been trying to understand and better study its properties. Let me just quickly go to my slides and see if I have anything about this real quick. Okay, I guess I don't. But if you do a search on Sagittarius Dwarf Galaxy, it will come up. And there are many at this point, dozens actually, of dwarf galaxies orbiting the Milky Way that over time will be assimilated into the Milky Way. And if you even do a bit more Google searching, you'll find that we are actually, at the moment, flying toward the Andromeda Galaxy, this thing. The Milky Way is going to collide with Andromeda in about 2 billion years, and we're all going to be part of the same galaxy. We will combine together into one larger galaxy at that time.
Our last question, what does learning about the universe teach us about life on our planet? What will happen to our planet in the future? And will life end when the sun cools, if it ever cools?
Okay, so here's what's going to happen. The sun is about 5 billion years old. And in about another 5 billion years, it's going to run out of nuclear fuel. So the sun is powered by nuclear fusion in the very center. And nuclear fusion is an incredibly efficient process. It converts hydrogen to helium. That's what's happening in the center of the sun. But sooner or later, that fuel runs out. And that's going to happen in 5 billion years. Will we be around to experience that? Maybe, maybe not. Who knows? But in 5 billion years, the sun's going to expand. It's going to become what we call a red giant. It's going to engulf the innermost planets. Mercury and Venus, and probably the Earth will be inside the sun. It's not going to be much fun living on the Earth at that time. I mean, every day will be a beach day. It'll be hot, right? It'll be sunny, very hot. Anyway, the point is that at that time, life on Earth will end. And that'll be pretty much close to the end of the sun's life. The sun will then have another few hundred million years or so after that before it ends its life. But that's basically the end of the Earth and the inner solar system. The other planets will be around, of course, Jupiter, Saturn, Uranus, Neptune. They'll be around to do their thing, but they'll be much different because the sun will get brighter and cooler at that time. And so their, the conditions on those planets and their moons will be completely different. And in the end, the sun will contract and become very small. It'll become the size of the Earth, essentially, into what we call a white dwarf, a very tightly packed, very dense object made entirely of protons, electrons, and neutrons, just basic subatomic particles. That's going to be the end state of the solar system. Now, what was the rest of your question, Michael? Was there another part in the beginning?
What does learning about the universe teach us about life on our planet?
Very good question. And I've been asked this a lot, actually. People ask, well, why do you do astronomy? What's the purpose of astronomy? And I really just have one answer, and that is, it's fun. It's fun. It teaches us about the universe. It teaches us about where we are in the grand scheme of things. It's for the sheer gathering of knowledge, the sheer application of science, and understanding and knowing our place in the universe. Now, don't get me wrong. There are some branches of astronomy that do have practical applications. We study the sun, obviously, so we know what the sun is doing. The sun's important for life on Earth. We study other planets, especially the gas giants, to better understand weather and how weather operates on large scales. So that helps us better understand weather on the Earth. But for the most part, we do astronomy for the sheer joy of gathering the knowledge and better understanding our place in the universe. And what it teaches us is that the Earth, that is a very fragile ecosystem. It's very small. It's very fragile. We look at planets like Venus, which is very hot, very, the pressure on Venus is very high. The surface temperature is 900 degrees Fahrenheit. It's very hot. Venus is a very similar, sized planet to Earth. We look at Mars, which is just outside the Earth's orbit. It's a little smaller, very thin atmosphere, basically desolate. We think there might be water on Mars, but most of it is pretty much desert. And so we conclude that these ecosystems are very fragile. And the Earth has been around for 4.5 billion years, but over that time, the climate has changed quite a bit from one, cold to hot and back and forth. But it does teach us that the planetary ecosystem is quite fragile. Also, of course, look at this picture of the Andromeda Galaxy. It's a beautiful object. It's colorful. It's organized. It's a pancake. It's flat. It's beautiful. It teaches us how beautiful the universe is and how organized and how ordered it is. And it really reminds me of Carl Sagan's original series, Cosmos, which means order. And when you study the universe, you really get a sense of just how ordered everything is and how everything has been put together in kind of an amazing way in terms of how things work together. And again, that's what science does. It teaches us about the nature of the universe and how things are put together and ordered.
All right. So we can stop sharing our screen, Ada, please. Thank you.
Okay.
So we want to thank everybody for joining us. We also want to remind everybody that MODS is committed to connecting you to inspiring science even through this challenging time. So please consider giving to MODS to keep science in motion. If you visit mods.org/scienceinmotion to support the museum's virtual programming. For donations of $50 or more, we'll send you a Joey the Otter. Hi, Joey. Plush, just to brighten your day. Even $5 matters. We look forward to welcoming you and your family to MODS real soon, and to the AutoNation IMAX Theater to watch movies like Hubble in their full glory.